Today, we will go through the third part of the optimization of LLM performance series, and we will go through the topic of introduction to retrieval augmented generation. Let's do a quick recap of what we have covered during part two. Part two, we focus on context engineering and we discussed the importance of context. LLMs are limited by its parametric nature. That means behind an LLM, essentially, it's a very large matrix that is fixed once it's trained. And these parameters are learned by the data that was fed into the LLM. Once it's trained and cut off, all the knowledge after the cutoff date will not be known by the LLM. So providing context to the LLM will be very important to make sure that LLM doesn't make up things if we ask the LLM to answer some questions that it doesn't know of. But real-world applications are really knowledge intensive and time sensitive. So by just feeding static context into LLM will not be sufficient. Last lecture, I introduced some techniques of context engineering that takes in wide range of sources of information and then perform some techniques like filtering and then context compression and application of multi-agents to fix the context such that we avoid the notion of context explosion. That means we avoid the length of the context to go above the context window limit or to have a very high cost when we perform inferencing. Okay, today we will introduce this concept of retrieval augmented generation, which is system of context generation technique. Okay, this is an overview of how retrieval augmented generation works. When a user passes a text query, instead of asking the LLM to generate the text directly, we will let the LLM or the same or a different LLM to search a knowledge base. And through some technique, we will retrieve the relevant context from that knowledge base and use the context to augment the original query to form a prompt to pass into the large language model and generate the text response. So RAG is an architectural paradigm that enhances the accuracy and reliability of the generative AI. Let's look into how the system works. Here is a slightly more in-depth workflow of a RAG system. When a user asks a question, an LM will perform a search or an algorithm will perform a search into a vector store, which is like a database of embeddings of the text. And based on some search algorithms, such as similarity or TF-IDF, that based on keyword search, we will retrieve some chunks of knowledge from the knowledge base. And then these chunks will be passed into context. And the context and the original questions will be merged into new prompt with some prompt templates. And then this new prompt will be passed into the large language model to query and thus its inference. And the inference will be processed into an answer that pass back to the user. RAG system dynamically retrieves relevant information from an external knowledge base on the fly and provide this information to the large language model as context for generating a response, ensuring its outputs are more accurate, timely, and contextually relevant. So at its core, a RAG system is composed of two primary components that work in symbiosis. It's the retriever here and the generator here. So essentially, these are two sets of tools or AI models that convert this content to the next stage from query to context, and then it continues to convert context to response. So the retriever here works as such. Okay, given user's query, it performs search through a vast external knowledge base and fetch a small subset of documents that are most relevant to the query. And then the generator, typically it's a pre-trained LLM that takes the original user query and the context provided by the retriever as an antonymy of RAG. So here, this is like a legal court example where you can imagine the retriever is like a clerk and the generator is like a judge. The user query is like a court case where somebody raised this case. The clerk will help to process the law precedents, the case files, and the evidence presented by perhaps the lawyers and the witnesses. All this information will be sorted out nicely to be passed to the judge. And the judge will review all these nicely structured and formatted content and to do the ruling of the case. So in this scenario, that is removing the clerk and the president's like the information. We are essentially asking the judge to just look at the court case and base his or her memory to make the ruling. This is suboptimal because it depends on the judge, long-term or short-term memory, and the memory may have faded off, or some of the contents may be mixed up between fact and maybe some of the opinions. So this will not be objective and fair. Okay, so we can see that the key benefits of RAG listed here. So first, the main objective of this is to reduce hallucinations, significantly reduce the likelihood of hallucinations, allowing user to verify the sources. Okay, the second benefit is that it's timely. So the external knowledge base can be continuously updated with new information without the expensive and time-consuming model retraining. The third advantage is domain adaptations, where it enables a general purpose LLM to function as a domain-specific expert by connecting the LLM to a curated knowledge base. And finally, we can achieve data privacy by providing personalized response, securely accessing a user's private data, such as email, notes, or project files, without having the LLM to know this data. All this will be stored in our own, can be stored in our own on-premise devices, and the LLM does not have access to it. So here is a screenshot that shows ChatGPT that answer a query with search. When it generates its response, the citations and the sources are all listed. Okay, next, let's move on to the RAG workflow. So in general, a RAG system comprises of 5 components. We have seen the documents, the knowledge base, vector store, retrieval algorithm or retrieval engine, and the generation engine or model. Typically, it has multiple sources and come with multiple types, unstructured or semi-structured manner. So the documents can be your PDF files that they stored in your computer or in your own file storage. It can be web contents that is live on the internet that you have a tool to access in real time. It can be some code bases that resides in your computer or in, say, GitHub or in your private repository. And it also can be some chat logs that resides in maybe your internal instant messaging apps or some logs that you in the system. So all these content typically come with different forms. So merging them is very tedious and challenging task. So later when we look at some case studies, we will know why is that. The second component is the knowledge base. So from all these sources of data or the documents, we will first process them nicely and then merge them into some structured format and then cut them into small chunks and put them into a database. Okay, so all these are now sorted, cleaned, deduplicated, and then put it and stored efficiently in some knowledge base. This can be SQL database or it can be something else like knowledge graph that is more and more popular. After the documents are processed and then split and saved in the knowledge base, the next step is to process all these chunks into the embeddings, which are vectors that represents the hidden meaning of each chunks. And then all these vectors, which is a sequence of numbers, are then stored in vector stores. Okay, so a vector stores can be another database system. The modern database like MongoDB that it offers the functions to store vector data, and even PostgreSQL allows us to store vectors into its relational tables. There's a third component, the vector store. So when our user pass in a query, we will need some components to retrieve the relevant content. The retrieval is a set of algorithms or models that look at the user query and then try to search relevant information to the query, first from the vector store, and then through the vector and chunk pairing, it will get the relevant information and put them together and format them nicely to form the context that will be passed together with the original query to form a new prompt and pass to the LLM for generation. And finally, of course, there's this generations components where the prompts that is formed by the context and the original query, and this is passed into the large language model for generating the final response. Okay, so that is the basic workflow that consists of these five components. Okay, so the next part, we will talk about how to evaluate a RAG system. As we see that this is a system of five components, but every step it can consist of many contents and the process of it can be challenging. So the effective evaluation of a RAG system cannot be simply evaluating the output of the large language model. Okay, so it requires a robust RAG evaluation system that evaluates all these parts, either from components to the process of converting the content from one component to the other, and also the end-to-end outputs of the whole system. And all this needs to be done systematically. So now let's dive into what can be done to better evaluate the RAG. Okay, so typically the evaluation can be by components, right? And also can be end to end to evaluate from a user query all the way to response. Okay, so here comprehensive evaluation strategy employs matrix for key parts of the system. Okay, so now we can dive into each part of it. So first, the knowledge matrix evaluates the efficiency or the effectiveness of converting our content from documents to the knowledge base. Okay, so the documents are the raw information we get, like the chat log, like the web content, like our data, our code base, etc. Okay, and then the knowledge base essentially the chunks that we have processed, formatted, and then split and saved into well-structured database. So the knowledge matrix measures the effectiveness of converting the raw documents into this structured format. The retrieval matrix essentially measure how effective the content in the vector store to the content that is retrieved outside of the vector store. Essentially, it measures this process, the effectiveness of this process. And of course, the generation matrix measures the effectiveness of this generation, the generator like GPT model or other generative AI models, and how is the quality of this generation. But this sounds simple, but later we will see this is slightly more profound than this. For instance, if we think of how do we know the response is good, it's not just about accuracy because we care less about how the generated content is exactly similar to the desired contents word by word. We care more about whether the content makes sense, whether it's fair, it's harmless, and it's complete, right? Measuring the quality of it is a much more profound task than measuring the accuracy of it as compared to general machine learning task. Okay, so first, let's look at the knowledge matrix. As we mentioned, the knowledge matrix measure the effectiveness of the data being converted from the raw form and from various sources to the structured form of knowledge base. So measuring such is determined by how information in the knowledge base is processed and structured, right? Because there are multiple steps that are taken to convert this knowledge. So we need to know either all the steps together achieve some level of competency in the knowledge base, or componentally which steps are performing better than the other. Okay, so the matrix generally used this context recall and context relevance. Context recall essentially is answering this question of whether the chunks inside the knowledge base contain all necessary information, and context relevance essentially assessed what proportion of the chunk is useful. Okay. Next, for retrieval matrix, essentially we are measuring how effective the algorithm here or the models used here is able to get the right information we want. This is very relevant to a domain or to a research community called information retrieval. Information retrieval essentially studies the effectiveness of retrieving information, or rather the algorithms or proposed models that tries to retrieve information from some sources more effectively. So typically we use matrix that are used in the traditional information retrieval community. Okay, here are three accuracy matrix, and this is more computational performance matrix. So first, we will measure recall at K and precision at K. If you learn statistics, you know that this is formulated by the true positive, true negative, false positive, false negative of the predicted values and the ground truth. Recall at K essentially measures the coverage of the retrieval. That means whether the LLM or the models or the algorithms retrieve all the relevant documents or all the relevant informations from the knowledge base. This focus a lot on the coverage, relevant information is retrieved, whereas the precision of K measures the noisiness of the retrieval. That means out of all the documents or information we retrieved, how many pieces were actually relevant? These two measures the performance of the retrieval from different perspective. In typical classification task, we also measure recall and precision, but more often we will use, say, accuracy and F1 scores to indicate the performance. But here, when we do retrieval, we tend to use recall and precision more frequently than accuracy and F1. Okay. And the next one is MRR, which stands for mean reciprocal rank. This essentially answers the question of how high up in the rank is the first relevant document averaged over many queries. This is also a quite direct measure of the performance of the retrieval matrix. So these three are very commonly appearing in many reg papers. And lastly, there's this computational performance matrix that is very important for industrial setting or for production level system setting, which measures the performance of the vector store. That means when we actually deploy the database of vectors and also the algorithm that on demand retrieve information, we want to assess the compute resources required to retrieve some information from here, and also the efficiency, or rather the speed that retrieve all this information. Some of the common metrics are used: query latency, how much time it takes per search, and queries per second, indexing time, which means the time to build the search index, and the memory footprint, which means how much RAM is consumed to perform the retrieval. These are extremely important to be measured in a production level system, because in practice, every retrieval costs some money, The larger the system or the larger the user base, the more queries will come in and we need to queue up. So first, we don't want each query to take too much time. And second, we don't want too many queries to queue up for too long, which directly link to users' satisfaction and also loyalty and whatnot. So this is a very important matrix if we look at production level system. Okay, and finally, we look at generation matrix. Okay, here is an overview. Later, we will go into more detail in some practical systems of generation matrix. So evaluating generated text is very challenging, as we discussed earlier, right? It cannot be simply measuring the accuracy of it, because what we care is not how many words matching the ground truth for the generated response, but rather we want to know whether the response is grounded, it's faithful to facts, right? Does the answer contradicts the source? And we also want to measure the generated text is to the question, right? So all these are secondary matrix to measure so-called hallucination. And there are multiple systems of matrix that are used to measure different stages or different components of the RAG system. Here, we will introduce three of the systems of the matrix that's widely used and well regarded in the industry. The first one is called triad of matrix, which is commonly used to measure the hallucination of a RAG process. The second one is called sense making. It measures whether the generated query makes sense or not. And finally, the last one is constitutional AI. So this is proposed by Anthropic, which is the company that builds or train cloud, which is one of the highest performance LLM to date. So this generally measures the harmlessness of the RAG output. Okay, we will go into greater detail for each of the system. First, we will start off talking about the RAG triad. So as we discussed, not just the outputs, but the RAG process may suffer from hallucination because oftentimes when the retriever retrieves information, it can be insufficient or it can be irrelevant, right? So if it is insufficient, recall at K will be low, and if it's irrelevant, that means the precision at K will be low. We need to know whether the retrieved content is sufficient and largely relevant so that the generated response will not be a result of hallucination. The triad is designed to measure the conversion among the components to evaluate the hallucination in the process of a RAG system. Here, we have three main components. They are content relevance, they are groundedness, or also known as faithfulness. And lastly, it's the answer relevance. So context relevant essentially measures whether the retrieved content is relevant to the query. So it's the measurement of efficiency of this edge, of this link between query and context. Faithfulness or faithfulness measures whether the response is supported by the context. So it measures this edge between the context and the response. And finally, the answer relevance, as the name suggests, is to measure whether the response is relevant to the query. This is one system of measuring the hallucination of the RAG. The next system is to measure the sense-makingness of the output. Just now, the one we measures the process, and now we start to measure the output. Instead of measuring the accuracy, which is pretty naive, we measure the quality of the outputs in three different dimensions. In fact, typically we measure four. There's an overall dimension that is weighted average of this field depending on the actual task we want. Defining ground truth for many RAG queries, particularly those involving complex high-level semantics, poses significant challenge to address this. Okay, so generally, we first measure the comprehensiveness. So whether the response is comprehensive, that means how much detail does the answer provide to cover all the aspects and detail of the question. The second dimension is diversity. So, how varied and rich is the answer in providing different perspectives and insights on the question? And finally, we measure the empowerment, which states how well does the answer help the reader understand and make informed judgments about the topic. Okay, although the matrix states all these different aspects, but the actual quality of it really depends on the setting of the large language model, as we experienced in the previous lab. When we deploy the large language model to perform generation, we can control the temperature and entropy to control the diversity of it. If we change the temperature to close to zero, we are expected that the diversity is less. And if we ask the LLM to generate a shorter response, the LLM will be forced to generate a less comprehensive solution, but instead a more brief answer. So the actual value of the matrix depends on our setting. And of course, it depends on what we want for the actual rec domain. Okay, so this is the second system. The last system, which is getting more and more attention, especially from the policy making and government side, which is the Anthropic's constitutional AI principles. So this constitutional AI essentially measures these HHH principles, which stands for honest, harmless, and helpful. And this is actually the core values of the formation of Anthropic, this company, where the founding team was unhappy with the way that OpenAI was training the model and releasing its product. So they formed Anthropic to build really harmless AI that strictly follows these constitutional AI principles. So these are essentially high level matrix. To measure that, there are a lot of subcomponents to it. This is one system of measuring the H3 components, and this is implemented by TrueLens. TrueLens is one of the most popular or famous open source toolkits for measuring the RAG system, or rather for AI agents' performance. And TrueLens has a dedicated library or set of classes implemented to measure this HHH system. Under honesty, there are answer relevance, embedding distance, context relevance, groundedness, summarization quality, and customer evaluations. For harmlessness, we look at PII detection, then toxicity, stereotyping, jailbreaks, and custom evaluation. And for helpfulness, we measure the prompt sentiment, language mismatch, conciseness, coherence, and other custom evaluation. So these are beyond just subsets of matrix, but they are functions and interfaces that can be extended to our system. So in practice, when we use this class from TrueLens, we can further extend how it works. And many of these measures are actually run by separate calls to LLMs. So measuring all these not necessarily done by algorithm, but it can be done by calling another large language model and let the large language model to judge if the query or the response falls under this measure or meets certain threshold of the matrix. So if you're interested, you can take a look at this paper. So this link leads you to the original constitutional AI paper released by Anthropic. And this link leads you to the documentation page of this implementation for TrueLens. Okay, to measure the RAG systems performance with different systems, with different evaluation systems, oftentimes we will just use open source tools. Okay, and they come with free access. They are released in GitHub. These two are two of the most popular evaluation system. The first one is called Ragus. So Ragus have easily 15,000 stars in GitHub. And TrueLens is also another one that is very widely used to measure the performance of the rack system. During the lab, we will use a bit more on the true lens. If you are building your project and then you want to measure some systems that true lens doesn't offer, you can potentially check out Regus and measure the performance. The next part, we will talk about some industrial rack application and to witness how the practical considerations we need to have while developing such useful applications. And we will also go through some high-level implementation of the rack system and the learning that we can get from it. Now let's get started. Okay, practical rack systems require optimizations in all components that we earlier mentioned that there are five components, but implementing it's very simple. Sometimes we call it naive rack, but it doesn't actually solve real problems because in real setting, there are many constraints such as data availability, cost, and some limitation in data governance, and also availability of the data, compute resources, etc. So when we put practical consideration into building such rack system, the kind of problems that we need to handle is much more profound. Here you can see that later in the case studies, we will see some scenario has very limited data and getting those data is next to impossible. Okay, and also we can implement some rack system, but the quality control at production level is very hard or very expensive if we do it extensively. And also, when we are able to build a rack system in terms of functionality, when we deliver the result of the rack system to the user, there are also a lot of production and user interface and user experience considerations that we need to take into. So in practice, when we build a rack system, it's not just about making it work. There are a lot of considerations that we need to take into. Next, we will show how existing companies innovate to build their rack system to solve specific problems. Today, we will go through four cases from different companies. First, we will go through, okay, the sequence is a bit, okay, I sort the sequence. So the first case, we will go through Shopee implementation. And then the next one, it will be LinkedIn, Pinterest, and DoorDash. Let's jump into it. The first case study, we will look at Shopee, and the system is zero-shot rack for multilingual intent classification. The main challenge that Shopee is trying to solve is that they have a lot of markets. So essentially they cover 11 markets that covers six languages. And the chatbot they have has tons of conversation, right? But typically, if we think about it, when a customer come to Shopee and then try to talk to chatbot or talk to customer support, they definitely come with some purpose, or we call it an intent. So knowing the intent will help us or help the LLM solve customers' problem effectively. Because no custom, very little genuine users will go and talk to a Shopee chatbot for how's the weather or just some chit-chatting. It will come with a purpose. This become a very crucial task, but to solve this task, it's very challenging. Why? Because knowing the intent is hard. It requires a lot of manual labeling. So internally, Shopee has quite a large amount of intents, but they are all singleton. That means if the user says waiting for a long time, there will be labels that says this could be a complaint. Okay, but they don't necessarily have multi-turn dialogue intents that are labeled. This is an example. If a user come in and say waiting for a long time, it will be classified as a complaint. We think that like this user is complaining essentially, or the LM thinks so. But if we put this into context, if the user first say, I want to get my order, essentially this may mean that the user wants to know when he or she will get their order. And then he or she further explain they have been waiting for a long time. So with this, the correct intent of the user could be to expedite the delivery instead of coming in to complain. Okay, but if we just use the singleton intents from the existing database, this intent can be wrongly classified, which lead to irrelevant generation of the LLM. So that is the setting. But to get these labels for multi-turn dialogue intent, it's very hard. First, it's very expensive to hire people to do it. And also the intent not symbolic. It's not just class one, class two, class. The intent contains semantics, like it contains meanings, like textual meaning to it. Like here, expedite the delivery. So all these are formed by words, and the sequence of words comes with meaning. So class putting asking people to label the intent is very, very time consuming and expensive. This is actually the core challenge. The core challenge is not to just use RAG to generate a response, but to actually find out what the user wants before generating an intent. Before generating a response or a call to action. The solution here is this notion of LARA. Okay, so LARA stands for Linguistic Adaptive Retrieval Augmentation. This framework essentially is designed to enhance the accuracy in multi-turn classification task across across the six languages that accommodating a large number of intents in the chatbot interaction. There are three main stages. First, we will do a candidates selection here that we use simple and pre-trained model to analyze the conversation to predict a small set of possible intents. And then we perform in-context learning retrieval. That means we provide instruction or we provide examples to retrieve the relevant demonstrations from the intent database. Okay, and then we perform the prompt construction here that is combined with the original conversation and the demonstration to generate the intent. Okay, so this whole process is designed to save costs, of course. So instead of asking people to label multi-turn intent, it uses RAG to artificially augment the original conversation by adding the multi-turn intent from a singleton database. So this is where the core innovation of the system come from. How it works, let's walk through how it works. First, there's a phase one. So the phase one is to perform candidates intent selection. That means there are multiple intent options that we can choose, and then we will retrieve all the possible candidates using a very small classification model. Okay, so first we will have the conversation, right? This is an utterance between a user and an assistant or a model. So first, we will combine for each utterance the user's input and the final query. Here, hello, and then the second utterance, the query from the second utterance, can I cancel my order? And then the last utterance, and so on and all the way. We will first combine the query in this way, and then we use this combined query to perform a singleton classification. And then we will retrieve some candidates intent. Let's say for this one, it sounds like a complaint. So we will retrieve complaints intent. And then this one, can I cancel my order? The intent could be request to cancel order and so on. We will have multiple intents. So all this will be put in as a sample retriever. This is the next phase. We do combine query and then we do predict candidates. So that's the phase one. Phase two, we will perform ICT retrieval. So ICT stands for in-context learning. So that means without fine-tuning the model, we will just do prompt engineering by giving an instruction or giving examples. We've gone through this in the previous lecture during context engineering that ICT has zero shot and few shots. So we use some prompt templates that perform ICT retrieval here to retrieve examples from the singleton examples or singleton library. And then we will proceed into here. So we will convert the examples into embedding, and then we Here we will combine all the user queries. So here there are four utterance, four exchanges. So we just take all these four. Hello, can I cancel my order? I haven't received it. Wait for a long time. Okay, so we combine this, and then we vectorize it into its own embedding, and then we try to use similarity score to rank the top demonstrations. Here there are intent samples. This is the combined query, and then we will rank them based on the similarity. There's a finding a similarity demonstration. Okay, and then the phase three, we will construct the prompt. So this is the straightforward ones. Okay, so we have the query and then we have the intent. So we will pass the query and all the candidates, the demonstrations candidates into prompt templates that forms the prompt, and pass the prompt into the LLM, and then let the LLM to choose the most appropriate intent to be used for the original multi-turn conversation. This is generally the how the whole Lava system works. Okay, what are the learning points from these examples? From the results perspective, Lara enables a state-of-the-art performance without new annotation, and this is much harder than it literally means. Generally, like if you want to improve anything like models performance in any aspects, one of the way is to improve the quality of the data or the coverage or the quantity of the data without changing data and without changing the coverage of the data and without adding new labels. To make the performance better, it's actually require a lot of innovation, a lot of engineering work to do. By achieving better performance without adding new annotations or new labels, that saves a lot of money that otherwise Shopee has to invest. And we see that this RAG system is applied as a data augmentation and cost reduction engine rather than a RAG for generation. So that I hope it's an eye-opener that RAG can be applied in a small components in a larger system rather than having to be the entire system itself. We can see that it uses not just to answer the question, but just in the middle, more accurately retrieve the multi-turn intent so that another LLM can better answer the user or help the user to perform some task. And empirically, it dramatically reduces or eliminates resilience on expensive data annotation pipeline that otherwise will incur a very high cost. So it lowered the cost and accelerate time to market for new AI features. So that is the end of the first use case. The next use case is also an application of RAG in data processing. So this is a case study that is reported or released by LinkedIn. LinkedIn is one of the largest social network for professionals. If you haven't created a LinkedIn profile, I suggest you create one because it will be good for you to build up your network. The problem that LinkedIn is trying to solve is the failure of unstructured retrieval. Here is screenshots of Jira system, which is a project management tool. It records the supporting tickets that LinkedIn internal or external users raised. So let's say a user has an issue, it will submit a form or write in, then the system will automatically create a record here that someone has raised some supporting tickets. What is the content and who is in charge of that particular ticket? Okay, for a simple RAG to handle Q&A that is linked to a database like this with unstructured data, there are multiple problems. First problem is loss of vital structure. So if we treat the tickets as simple bag of text, that means if we merge all these texts into a single string, we essentially ignore the inherent structure. Some fields are relevant to some other fields. Say the type and maybe the inside content is relevant to the summary. But if you just merge all this in or concatenates all the phrases into a single string, we lose the information or we lose the relationship among the fields, which make the retrieval much less accurate, or rather increase the probability of having RAG hallucination. Okay, And also, there's a logical fragmentation, right? Splitting long tickets into fixed size chunks often separated a problem description from its solution, which leads to incomplete and useless retrieval information. So essentially, overall, LinkedIn wants to build a system that can preserve and exploit the rich relationship structure of the data beyond the semantics of the data. That means literal meanings of all these text fields. That is what LinkedIn wants to achieve. The solution of it is what this illustration suggests. It's a dual level knowledge structure. So there are two phases here. The first phase is this offline knowledge graph construction. Okay, and then the second phase is the online retrieval. And by saying offline, that means this is done before the system is live. And when we say it's online, that means this is done while the system is being served to its users. Now let's dive into it. The phase one is the offline knowledge graph construction. So we can see that it starts from here. Okay, step one is pass and structure. Each ticket is passed into a tree, preserving its internal structure. Here it says summary, and then we have description, and then there are some fields. A ticket will be passed into a structure, and then you will try to connect the tickets together. So here there are other tickets. So it will try to clone from and to with existing tickets. Okay, so these are the inter-tickets connections, and we try to get the tickets and then connect them with previous tickets by the similarity between the tickets. So there is the second part. And then the third part is to perform embedding. That means vectorization of the semantic content and convert them into vectors and save in its vector store or vector database. So that is the phase one, okay, which is this side. For phase two, it will perform online retrieval and question answering. So given a question, so say this is a question that a staff ask or user ask. First, it will perform some entity detection. It will call an LLM to generate a summary of this task and to classify the priority of this task and also the root cause of this task. And then it also use LLM to classify the intent. Then based on this, it will perform a search from the knowledge graph where it will try to retrieve the tickets that process similar attributes to all this information. Let's say there's a ticket that has a very similar summary and then it has the same priority, same cost, and same intent. It will then retrieve that particular ticket. And of course, it can be more than one ticket. So it will be a list of tickets that is retrieved by the secondary contents that is generated by the original content. And then we will be able to retrieve the relevant tickets automatically without considering the concatenated text originally from the table. And after that, number six, we will then generate the answer by putting the original question, the secondary information, and the relevant tickets. Okay, we'll put them into a prompt template, form a new prompt, and then pass into the LLM to generate the final answer. We can see that the reg is applied in the middle. This is more complex kind of knowledge base we used to do data representation and data storage. And also the retrieval is by its secondary data. That means the information that is derived from the original primary content. That means we want to retrieve this by using this, but instead of directly doing that, we generate the secondary contents and then try to find similarity among the secondary contents and then retrieve the primary content based on the attributes of them. There is an advanced RAG system that enhance the process of retrieving information from unstructured data. Okay, what can we learn from it? Okay, for structured data, structure itself is the information. Just now we see that on the table, the actual information goes beyond just the semantics of each row, but the structural relationship also contain latent information among them. For enterprise data like tickets, reports, or case law, conversational RAG actively discards business value by flattening the data. But a knowledge graph-based RAG system can be very helpful in pertaining the structural information for the knowledge base. Okay, and in this case, the success lies in accelerating human workflow. Empirically, the most important matrix was this 28.6% reduction in resolution time. When a query comes in, it solves the problem with 28.6% less time. That means the internal process is faster, there's less entropy in the internal operations, and as a result, the enterprise runs more efficiently. So this data proves that the goal of the enterprise RAG is not just generating more accurate text, but to make a higher level goal, to achieve a higher level goal, make the human experts more efficient and more effective. When we design RAG system or when we measure RAG system, we first need to measure microscopic matrix, but at the same time, we need to take a step further and measure the high level impact and influence when we deploy the RAG system. There is some takeaway from this case study. The third case study we will discuss is a technical implementation of RAG system from Pinterest, which is to implement an effective text to SQL RAG system. So for those who are not familiar, Pinterest is one of the largest social media that allows photographers or travelers to post their photos and share with others, and they could charge a fee for people who wants to use their images as contents for commercial use. Okay, the problem space here is to unlock data for non-experts. Okay, so let's take a look. The user here refers to some internal staff in Pinterest. The staff has difficulty in accessing Pinterest data warehouse, which are gated by significant skills barrier, right? That means not everyone is a skilled data analyst or data engineer that knows how to retrieve data from the right table, or rather, they don't necessarily know the actual structure or schema of the data warehouse. If the staff wants to perform some retrieval or do some generation by referring to the internal data warehouse, it does not have skill sets to get to the right place or get to the right information. Okay, so this is essentially a data bottleneck. This limited deep data analysis to a small group of specialists, preventing product managers, marketers, and others from answering their own questions. So this system essentially wants to help to offload some of the workload from the internal data analyst job. Okay, and a naive or rather a simple text to SQL tools fail because users doesn't know which data table to select and where the data resides, and they don't necessarily know what are the tables available, right? And as the company grows, as the user base grows, as the content base grow, the table and the schema of the SQL grows non-linearly, it grows exponentially. Any staff that is not data analyst or data engineer will really have trouble accessing the right information. Okay, so now let's look at how they solve. Okay, so now let's look at the solution. So the solution is a two-stage RAG. So now all the systems that we have seen so far, there are multiple stages, right? So the first one we have three stages, and then second we have two stages, and here there is also two stages. Okay, I hope that we can begin to see some pattern. All requires some offline process, and then there will be an online kind of process, which is the RAG supports for live system. There are also two stages. One is offline vector index creation, which indexes all the SQL query logs, the tables and content in the data warehouse. The second one is the live system, where it helps the user to generate the final query without necessarily knowing which table it goes to and where the content is. Okay, let's look at how the system actually work. Okay, this one, the process is slightly simpler. So there are 5 steps here. So in the first step, the offline job is employed to generate a vector of indexed of table summary and the historical query against them. We can see that the SQL query logs and the table meta will be passed into a prompt template, and then it will go into a large language model to generate the table summary, and then it will be converted into the embeddings, and then it will be saved into the vector store. So essentially, this vector stores the metadata of the table rather than the metadata of the tables in the data warehouse rather than the actual content of the records in the data warehouse. Once this is formed, now we can perform the online rec system to help the user to generate what they want, okay, which is SQL query. Here, imagine this is a product manager or a marketer. The second step, if the user does not specify any tables here, the user can just provide some high level questions like how do we maybe how these features perform last month. Once query is given, if it doesn't come with the table, the rec system will first go to search the metadata vector store by comparing the embedding of the questions and the embedding of the metadata. Okay, so there's a question embedding, and then based on the similarity search, we will find top n tables. So we will know what are the tables in the data warehouse that we should query. And then from the top n tables, along with the table schema and analytic questions, they are compiled into a prompt for the LLM. This come to here, this come to here. So it compiled into a prompt and passed into a LLM to retrieve the top K tables. And then the top K tables will be passed into the text to SQL prompt to form the LLM. But before we come to here, there's an additional human in the middle quality check here that was introduced. Okay, before we generate the list of top case table, list of top K tables will be passed to the actual user to validate if the user thinks that the tables are relevant enough to the analytical question the user asked. And if the user think it is, then it will proceed into passing the tables into the prompt template to form a prompt and pass the prompt into the LLM to generate the SQL query as the last stage. Okay, now let's take a look. May I ask about smaller firms that may not have access to this huge amount of data? Will they also benefit? Yeah, of course. So for instance, I can give an example of a company that I work with that is not necessarily very large. I work with these traditional electronic shops that have perhaps about 20 outlets in Singapore, about 10 people, including the management, warehouse staff, and marketing team. Essentially, what they want to do is to optimize the items they put in the store so that they can optimize their sales. Their revenue comes from twofold, right? One is the commission they take, or rather the profit they take by selling the products that they carry. The second way is to rent out the positions of the store to a particular distributor or a particular brand owner. Let's say Shocks or maybe Sony. Sony, they may want to rent a stand and then put their newly launched items for a rent. There are pretty complex rack systems that we implemented for such outfit to enable them to effectively run their simulation. Okay, so basically their profit optimization is done in a heuristic or in a simulation environment. And then the simulation needs to do in context or online retrieval of their previous store's layout and the respective sales records. By running the simulation and linking to their own database, it's able to save a lot of their costs by, or rather save them a lot of physical experiments in actually finding the optimal pricing strategy. That is like a real life example of the actual application of AI for a small setup? Or do you mean like even smaller than like a team of maybe 10 to 12 people? Or do I answer your question, Prof? Okay. Yeah. So nowadays there are reportedly a lot more one-man companies, like one man startup that use AI as assistants to do to automate like many of the business functions like marketing, customer handling, and then building the end-to-end sales funnel, and of course like for product development, for price optimization, etc. Even from a team of one, AI will be very helpful. That is something that I think there will be the trend in the future. Each person gets more and more capable in using different kinds of AIs, and the AI will get smarter, and then the markets will become more and more sparse because larger companies, although they have a lot of people, tend to move slower as compared to the smaller teams. So small teams always get quicker to market and then higher rates of innovation and etc. That is something that I think another aspect of taking advantage of the surge of AI. Okay, what can we learn from this case? Okay, so first, the most critical retrieval may be the metadata. That means what content, like files that describe what is the content of the data rather than the data itself. By looking at the metadata, we can actually optimize the performance of retrieval and optimize the performance of human level effectiveness quite vastly. Okay, this case also show that there's quantifiable link between data governance and AI performance. Okay, if the organization of the data as well as the dimensionality of the data are well structured, that means we have first order data and then we also have second order data, which is the metadata. So if we have them structured and well connected to AI systems, we are able to drastically improve efficiency of the company's operations rather than just looking at the systems itself. This is the second last case. And the last case we will go through slightly more quickly. Okay, the last case is reported by DoorDash, which is arguably the largest quick commerce company in the Western countries, in US, in Canada, in European countries. What they do is to use RAG to enhance customer support with AI guardrails. DoorDash is a quick commerce platform that connects consumers with local restaurants, grocery, and convenience stores for on-demand delivery and pickup. They are a funded company under Y Combinator. There are two problems listed here. First, they have a rigid and flow-based system at first, that the previous automation for customer support only handle a small subset of predictable dasher. So the dasher are the driver, leading to high escalation rates. Escalation means uplifting a conversation from talking to chatbot to talking to a customer support human. One of the goals of a chatbot is to reduce the escalation rate, because the whole point of implementing a chatbot is to reduce the need of human support while maintaining or improving the customer reviews or customer loyalty, right? Although this is like a support for drivers, drivers are their partners who are self-employed. Without drivers, they would not have buyers. So drivers are indirectly their customers also. So they also want to improve the customer's experience, like the drivers or the dashers experience, without having to hire a large team of customer support personnel to help them solve the problem. Okay, and also they have a large underutilized knowledge base. So as quick commerce generates tons and tons of data, but the data is not highly utilized as a valuable repository, because the dashers struggled to find the right articles to support their case. And also finding specific information within an article is also difficult, right? If you are driving, or if you're driving a bike or driving a car, you face some problem, it's impossible to click through the documents or flip through the articles to find the information that you want. Okay, and this kind of internal information is not necessarily retrievable by public LLMs, right? So to help the drivers to solve these problems, it requires an effective internal system, right? And also language barrier can be one, right? There are a lot of foreign talents that are working in the Western countries that are not necessarily very good in English, right? So they will also need to solve the language barrier. Okay, so here is their solution. Their solution is again a multi-layered system that is designed to generate, validate, and continuously responses. They have their RAG core, which is to generate a content-aware answer from the KB articles. KB stands for knowledge base. They also have the LLM guide rail. This is essentially their innovation. So the guide rails safeguard the evaluate or safeguard content that is generated by the LLM and make sure that they are relevant, they are helpful, and they are harmless, right? And also they implement LLM Judge that works offline for continuous monitoring and quality improvement for their cases and for their knowledge base. There's an offline system. Here they are using RAG mostly as a risk management. That means they don't want to generate forceful or irrelevant or unhelpful content that make their dashers more frustrated. For large consumer-facing brands like DoorDash, the primary concern is not just how accurate or how well the content is generated, but also how safe and how much it's aligned with compliance and reduce the liability of breaking it. So the needs of a complex guardrail and judge systems, a form of computational insurance that they invest in to protect the brand and migrate the legal risk. Okay, and also there's a trade-off between the latency and safety, right? If they implement a lot of checks in every stage, the time taken to complete a task will be very long. The system has to take into consideration the engineering tension. They implemented the two-tier guide rail as a direct architectural response to balance the user experience, such as having low latency with what the business needs, which is high safety. The implementation will be demonstrating a mature approach to a common RAG challenge. Dive deeper in how their guide will work. Here, there are two tier again. So there are two tier models that balance the safety with cost and latency. So here, this is the shallow check, right? So when knowledge base article is processed into the embedding, and then when the LM generates a response, it will put together with a segment similarity comparison and pass into some algorithm first to check whether the text is similar. This is generally checking the relevance, the answer relevance between the LM response and the knowledge base context, right? So one of the important metrics that we mentioned earlier in the evaluation. If it finds that the response and the supporting case is not so relevant, it will pass into another layer of guardrail to perform a deeper check. That is this notion of LLM as a judge. This will be passed into an LLM, of course, with some templates to check if any of the parts has a sufficient groundedness or faithfulness. So if this test fails, it will trigger some fallback. That means this text will not be sent to user, but instead this may be uplifted to customer support, or will prompt the user for some internal error or restart it again. So this is essentially how the two-layer safeguard works. What can we learn from this system? We have seen that RAG as a risk management measure, the primary concerns is not just correctness. Safety, compliance, and liability is important. Okay, and also we need to take into consideration the latency and safety trade-off. So while making sure the user experience is good, that means when the user asks a question, we want to generate the answer in the shortest time possible. We also need to meet the business requirements, that is all these safety, compliance, and liability measure. So beyond this, what is next in the RAG? So we have seen some emerging trends and future outlook of RAG, such as the rise of multi-stage RAG. Just the examples. All these examples are reported either in the past 2 years or some of them are very recently. We've seen that RAGs are growing from naive kind of retrieval generation process to very complicated system, and the system might only optimize a small components of a larger system, right? And it can be applied in different stages of the larger system, like from augmenting the data to doing risk management, right? To checking the quality of componental generation to perhaps doing some secondary validation of some algorithmic generation. Okay, and we see that the knowledge sources are getting more and more rich. The data can come from internal files, right? And they can be multimodal. So they can be text, it can be video, it can be audio records, like speech records, and it can also be structured data like the Jira tickets, right? So to process such knowledge sources gets more and more challenging, which shows us more and more opportunities that are yet to be grasped. And the centrality of evaluation, as the system grows more complicated, the measure of the performance of the RAG system gets more and more important and harder, right? So we know as a system become more mission critical, the industry standardized around comprehensive evaluation suites that measure not just the accuracy, but we have seen that the safety, compliance, groundedness, and user trust becomes the higher order goals that we need to implement the evaluation systems for. Okay, with that, I conclude this lecture.